All right, so we're going to look at a couple more examples of eliminating the parameter. You may have noticed that up until this point we haven't done any trigonometry at all. In fact, the topic of parametric equations up until this point may seem like it's something that belongs to an algebra class or maybe college algebra 372. This is where we start to fold in some of the trig, and it's nothing super complicated, but it does provide us with some really, really important examples of parametric equations. So what I want to do is eliminate the parameter where my equations are x of t equals 5 cosine of t and y of t equals 5 sine of t. And then once I've eliminated the parameter, I want to think about what the equation might be, or what the graph of these parametric equations might represent. One thing that we haven't been doing up until this, or we haven't been doing yet, but we will be doing more in section 10.7, is putting a restriction on t. So this is one of the benefits of parametric equations, is you can define restrictions on t, intervals that you want t to exist in, and that helps you control what piece of the graph you're graphing. So that'll make a little bit more sense in 10.7, but I could put something like this. T is between 0 and 2 pi. And you'll oftentimes see this written after a set of parametric equations. What this means is that if I were to graph these, I would only use values of t that live between 0 and 2 pi. Okay, again, that's going to be more important in 10.7. So let's try moving on to eliminating the parameter. We know one approach to eliminating the parameter is to try and isolate t. Now, I could try and do that. For example, if I wanted to isolate the t in this first equation, I would divide both sides by 5, and then I would need an inverse cosine. But the problem with the inverse cosine is that it has a restricted range, which would put a heavy, heavy restriction on t, something that we don't necessarily want. So it's actually not a very good idea to try to isolate t completely here. Let's start by doing what we've done every time and just write this as x equals 5 cosine of t and y equals 5 sine of t. Okay, so what I'm going to do here is, rather than solve for t, I'm going to solve for cosine of t and I'm going to solve for sine of t. So notice, if I divide both sides by 5, I get x over 5 equals cosine of t. And if I divide both sides by 5 here, y divided by 5 equals sine of t. Still doesn't seem like we have a way of eliminating the t. But this is where we want to use identities. That's the benefit of having trigonometry here, is we have a ton of identities that help us do away with some of these trig functions. I'm going to use the Pythagorean identity. From my Pythagorean identity, I know that cosine squared of t plus sine squared of t is equal to 1. But I have expressions for both cosine and sine of t in terms of x and y. So that means that this can be written, cosine squared of t can be written as x over 5 squared plus y over 5 squared. And that's going to equal 1. Let's simplify this a bit. This is the same thing as x squared over 25 plus y squared over 25 equals 1. And I could leave this in that form, or I could simplify it a tad more and notice that I have a common denominator of 25. If I were to multiply both sides of this equation by 25, I get x squared plus y squared equals 25. So what does that tell us about the graph of these parametric equations? Well, this should look very, very familiar. This is the equation for a circle centered at the origin with a radius of 5, the square root of this. This is what we would consider a standard parametrization, which means a pair of parametric equations that represent a curve. It's a standard parametrization for this specific circle. In Calculus 2 and Calculus 3, when you are working with parametric equations, oftentimes you're going to be told parametrize this circle and then use it in some other thing that you're doing in that class. This is the parametrization that you would oftentimes go straight to. However, as we're going to see towards the end of this video, generally a curve does not have a unique parameterization, meaning one curve can be parametrized in a ton of different ways. I'm getting a little bit ahead of myself, so we'll save that conversation for after this next example. All right, very similar looking parametric equations. I want to eliminate the parameter in this pair of parametric equations. So we're going to start this the exact same way. X is equal to 3 sine of t. Y is equal to 4 cosine of t. Notice this is the same thing as saying x over 3 equals sine of t, and y over 4 equals cosine of t. So again, the goal was not to isolate t in this case, it was to isolate the sine of t and the cosine of t. Now I want to use my Pythagorean identity to eliminate the parameter, because sine squared of t plus cosine squared of t is equal to 1. In this case, that's the same as saying x over 3 squared plus y over 4 squared equals 1, which can be written as x squared over 9 plus y squared over 16 equals 1. In this case, I'm going to leave my equation in this form. I don't have common denominators anymore like I did up here. So I don't want to multiply both sides by something to try and clear out these denominators. I could do that. I could multiply both sides by the least common multiple of 16 and 9, which would be 144, I believe, to clear these out. But there wouldn't be much benefit to that. Partially because if you look at this equation, this should also look familiar. This is the equation for an ellipse, which we learn about in intermediate calculus when you talk about, intermediate algebra when you talk about conic sections. So that's kind of the idea behind eliminating the parameter for us, is to put this in a form that's recognizable, and it's already recognizable here. All right, let's go ahead and move on. So I had talked a little bit about this, but what is parametrizing a curve? Parametrizing a curve, or parametrization, is what we're doing when we're basically doing the opposite of eliminating the parameter. Instead of trying to get parametric equations into the form of a rectangular equation, we're starting with a rectangular or a Cartesian equation and trying to get parametric equations that correspond to whatever curve this represents. So in this example, what I want to do is find two parametrizations for this curve. Now, I recognize this as the equation for the unit circle. And if I try to mimic what I did here, if you notice up here, we had a very similar looking equation, x squared plus y squared equals 25. If I compare that to these parametric equations that I had up here, x of t equals 5 cosine of t, y of t equals 5 sine of t, I can see that the coefficient on the cosine and the sine is the radius of that circle. So if I wanted to try and try to mimic this, the unit circle has a radius of 1. So this would suggest that if I set x of t equal to 1 times cosine of t, which is just cosine of t, and y of t equal to sine of t, then that would work. And I can verify that this would definitely work, because if I plugged cosine of t in for the x, sine of t in for the y, then what this would say is that cosine squared plus sine squared equals 1, which is true from the Pythagorean identity. But it said find two parametrizations. This is one parametrization. Again, a parametrization is a pair of parametric equations for a curve like this. So I want to find one that looks different but still represents the same curve. And there are, it turns out, an infinite number of different choices here. What I am going to try is this. X of t equals cosine of 2t. Y of t equals sine of 2t. This would also work as a parametrization. And the way that we check is we substitute, like we did here, these two expressions in for this first expression here. These are my answers. I'm going to show the check here. So if I plug cosine of 2t in for x, then that becomes cosine squared of 2t. Sine of 2t, if I plug that in for y, that becomes sine of 2t, or sine squared of 2t. And that is equal to 1 because the argument or the angle that I'm using in the sine and the cosine here don't matter as long as they're the same. If I have a 2t here, I should have a 2t here. That allows me to use the Pythagorean identity. Cosine squared of this angle plus cosine squared of the same angle equals 1. So these have different appearances, but they both parameterize the same curve. One thing that we could say about this one also is if you imagine the graph of the unit circle, we'll look at this more carefully in the next section, but this parametrization gives us a counterclockwise orientation for this curve. And if you plug in a 0 for t, for example, cosine of 0 would be 1, sine of t would be 0, which is going to correspond to the point 1, 0 right there. That's where t is equal to 0. As t increases, this point is going to trace out the unit circle counterclockwise. And it's going to do the same thing in both cases. But the 2t here means that we are doubling the size of t before we take a sine or a cosine. What that essentially means is that if you think of t as time, time is passing as this point traverses the circle, this parameterization is going to cause this point to traverse the circle twice as fast as this one will. But it still traces out the same circle. Okay. One last example. Here we're looking for two parameterizations for this equation, y equals x minus 3 squared. Now, this is a special case, and we encounter this type of case a lot, which is the equation that we're trying to parameterize is given in the form of a function. What do we mean by that? Well, what I mean is that one of the variables is isolated. Y is a function of x here. I can think of x as the independent variable and y as the dependent variable. Notice I could not have done that here. Neither variable was isolated, and if I tried isolating it, I would end up with a plus or minus square root of something in my solution, which corresponds to two different functions. Notice the equation also gives us a graph that's not a function. It fails the vertical line test. So this is the graph of a function. The easiest way to parameterize a function is to assign your parameter to the independent variable. So what I mean is this. X is my independent variable. If I let x of t just equal t, then t is going to be substituted for the x in this equation, which means y of t is going to equal t minus 3 squared. It looks pretty much the exact same as the equation that we started with, but the x has become a t now. That's the easiest way to parameterize a function like this. Sometimes, however, we want to take advantage of the form of the function to come up with a different parameterization. So I would like the y equation to look just a little bit simpler than it does right here. And one way to do that is to notice that the expression that I'm squaring is x minus 3. What if I let t equal x minus 3? So I'm assigning t to be the thing in the parentheses here. Well, in order to get a set of parametric equations, I need x as a function of t, so I would solve this for x, giving me x equals t plus 3. That means in my other parameterization, x of t can be written as t plus 3, right? However, what does y of t look like? Well, again, the point of this was to make y of t look simpler. And up here, if t is equal to x minus 3, then where I have an x minus 3 appearing in my equation, I can substitute t for that entire thing, giving me y equals t squared. And so both of these are valid parameterizations for the same curve. This is a parabola, notice. These would both give me the graph of a parabola, but I'm just representing that parameterization differently. So that's really important when it comes to parameterizations, and it's something that has some impact in calculus. Any given curve can be parameterized in more than one way, generally speaking. So it's important to be able to recognize two different parameterizations for the same curve the way that we have it here. Okay, so that's going to wrap it up for 10.6, and like I said, we're going to go more into the graphing part of this in 10.7.